As Steve has already mentioned, we are focusing on browser connectivity. We have for the probably last year, I would say. And I've given a talk similar to this about half a year ago at the P2P event in Paris. And things look very different there. So this is the updated version with all the progress we've made in the last couple of months. So as a very quick reminder, what do we do in libp2p? We connect nodes. These are point-to-point connections between two nodes. And because there's no one-size-fits-all, as we will see, nodes have different connectivity options. We use the concept of multi-addresses to encode the addresses of nodes. So there you can see two multi-addresses, one for a node that's listening on port 10,000 on TCP, and then a quick listener on port 20,000. All libp2p connections are secure. They are encrypted. There's no way to do unencrypted libp2p connections outside of like a testing environment. What does that give us? It gives us that nobody can listen onto our conversations, and it also gives us the nice property that we know who we're talking to. We know the peer ID of the remote. We use noise and TLS to secure connections. Like these are the two main options that are available to libp2p nodes. Every libp2p connection is also stream multiplexed. Once we establish a connection, and as we will see, this can be expensive in some situations, we want to make good use of that connection and have multiple protocols communicate in parallel. This is very easy when we use a protocol like QUIC that has streams on the transport layer. We don't need to do anything there. But when we use a protocol like TCP that doesn't have any streams, we apply a stream multiplexer to get a stream multiplexed connection. So let's look at the options that we have available. So as I already mentioned, we have TCP and we have QUIC. And that works fine for standalone nodes, like nodes that you would run on your computer or nodes that you would run in a data center. GoLibp2p has support for both TCP and QUIC. And as Max said, RustLibp2p will merge QUIC support very soon, thanks to Elena for her hard work on that. Unfortunately, in the browser, we can't just dial a TCP or a QUIC connection. Why is that? Under the hood, the browser dials TCP and QUIC connections all the time. Like every time you make a request to a website, the browser will either establish a TCP or a QUIC connection and then run HTTP on top of that. But the browser doesn't give you access to the underlying connection. There's no browser API to say, like, I would like to have just the TCP connection, but without HTTP. This is done mostly for security reasons. So one option that we had is using WebSocket. WebSocket is a pretty old protocol, and it's been part of libp2p for multiple years. I think very early on that was added. WebSocket is a protocol that allows the browser to establish an HTTP connection first, and then basically convert that HTTP connection to a TCP, back to a TCP connection, like to a full duplex byte stream. This is possible via HTTP1 and also via HTTP2 since 2018. So the way this works is you can use this JavaScript there, type new WebSocket and the URL, and the browser will then send a so-called upgrade request. It's a normal HTTP request with the upgrade header. And if the server is willing to accept this request and accept to speak WebSocket on this connection, it replies with an HTTP 200 code, and from then on, everything sent on this connection is not interpreted as HTTP anymore, but it's just raw bytes. And both endpoints need to make sense of these raw bytes. Which means we can, in libp2p, we can just treat this as a normal like TCP connection and run our Handshake on top of that, run a stream multiplexer on top of that, and get the properties of a libp2p connection that we want. We use the noise handshake to verify peer IDs. That works fine. It also means that we'll do double encryption if we have an underlying secure WebSocket connection. We have the TLS layer, and then we have the noise layer on top of that. So that's not great for performance. It works. The big problem with WebSocket, though, is that the browser will force us to do a secure WebSocket connection. So what exactly is a secure WebSocket connection? It's basically the same as a WebSocket connection, but we are running on top of HTTPS instead of HTTP. So there's an additional TLS handshake happening at the beginning before we send our HTTP upgrade request. And this poses a big problem for us in libp2p, because the browser doesn't only require this connection to use some certificate, but it actually forces us to present a valid certificate, like a certificate that was signed by a certificate authority, like Let's Encrypt, for example. But then Let's Encrypt doesn't just give us, wouldn't just give us a certificate for an IP address. To get a certificate from Let's Encrypt, you actually need a host name. And most libp2p nodes don't have a host name. It's just something that you might spin up on your machine or on some virtual server that you just booted up in some cloud environment. And you might not have configured a DNS server. So getting a TLS certificate for any libp2p node is just not feasible. There's some nodes where it is, like our bootstrappers, like long-running nodes where you put in the time to do some manual configurations. They can use WebSocket, but for the average libp2p node, it's not possible, and that's why WebSocket is like a fringe transport in libp2p. The other problem with WebSocket is that it's pretty slow. I did the math to calculate how long it takes to establish a WebSocket connection, and it's not pretty. You first spend a round trip on the TCP handshake, then you spend another round trip on the TLS handshake, then you do the WebSocket upgrade request, it's another round trip. Then we are in libp2p land, then we do a multi-stream negotiation of our security protocol, where we negotiate noise. Another round trip, then we do the noise handshake, another round trip, and then we negotiate the stream multiplexer, yet another round trip. So we end up with six round trips. That hurts. The only thing that we can improve there is the libp2p part. So we've been actually working on eliminating those two round trips we spend on this multi-stream negotiation. So we can, in principle, bring this down to 4 RTTs. But 4 RTTs is still a lot. Okay, so to summarize, WebSocket, it's an option. It requires a certificate. It requires manual configuration. But it was the first protocol that allowed us to connect browsers to the libp2p network. So a lot of time passed, and then at some point, WebTransport came along. It's a new protocol that's now being developed by the ITF. There's no RFC yet. It's still in the process of becoming an RFC, and that will probably take another year or two. It runs on top of HTTP3, which means, and HTTP3 is running on top of QUIC. By virtue of running on top of QUIC, it is always encrypted, and it provides access to the native QUIC streams. So it's somewhat similar to WebSocket, which gave you access to the underlying TCP connection. In WebTransport, we get access to the underlying QUIC connection. It also works, like on the wire, it's a totally different protocol, but conceptually, it's quite similar. So you also say, like, new WebTransport, you give it the URL, the browser will send an HTTP request, like an upgrade request that's encoded totally different. But then the browser can accept this, say, yes, I'm willing to accept the WebTransport session, and then you can use native QUIC streams. The security properties that the browser enforces are the same as WebSocket. At least that's what we thought until the beginning of the year. But then the W3C, which is the standards body that's standardizing the browser API, introduced a new option. And it's originally intended for short-lived virtual machine deployments. And these virtual machines basically have the same problem as libp2p nodes. They might not have a host name, and they also, because they are so short-lived, it doesn't really make sense for them to get a TLS certificate. So what the W3C proposed as a browser API is what the browser could accept a certificate that is not signed by a CA if it knows the hash in advance. So what the browser does is it just establishes the connection, does the TLS handshake, and then it calculates the SHA-256 hash of the certificate, and if that matches the value that it expected, then it will accept this as a secure connection. So in libp2p, we can use that. We already have multi-addresses, right? And we can put stuff into multi-addresses. And we do this by just adding the hash of the certificate to the multi-address. So now, if I give you a multi-address like this, you will know the port, the IP, you will know that it's WebTransport, and you will know the hash of the certificate. So your browser can establish a secure connection to me. There are a few caveats here. The API says like the certificate must not be an RSA certificate. Okay, we don't care about this. We don't use RSA certificates anyway. But it also says the certificate must be short-lived. Because this is only intended for these VM deployments, the certificate must not be longer than valid for longer than 14 days. And if you try, if I set up a server with a certificate that is valid for like 15 days, the browser will say like, nope, I don't accept this, handshake failed. So we need to work around this, and we do this basically by having every node generate multiple certificates and shipping multiple certificate hashes. And then when a node is very long running, if it runs longer for like 2 weeks, we just generate a new certificate and update our multi-address and advertise that updated multi-address to the network. So this all works. We shipped this in the latest Go libp2p release. Currently, it's an experimental status, but we will probably make this a default transport soon. So let's count the round trips here. We have one round trip for the quick handshake. We have another round trip for the WebTransport connect request. And then we run another, we need to run another handshake, a noise handshake, to verify the peer's peer ID. So in total, these are 3 round trips. But we can probably get this down to 2 round trips. Currently, the browser API doesn't allow us to do to run the noise handshake in parallel to the connect request, but from the protocol specification, this should be possible. So now it's basically up to the W3C to modify the browser API, so this is possible. And I'm hopeful that this will happen. I can't make any promises, but it's a protocol and an API that's still under development. So we can influence this, and we can probably bring down this handshake down to just 2 RTTs, which would be super great. Another thing I want to point out, we are running the noise handshake on a single stream. And then we can open more streams on this connection. This means we don't need to do double decryption, because the noise part is just limited to this one handshake stream, and after that, all the other streams are just encrypted once as part of the quick connection. So what are use cases for web transport? There are a lot of use cases for this, and I can probably not think of all of them. So I need your help here. But I have a few ideas that I've listed here. So one thing we could do is we could make applications like Glyph which are basically a way to send Filecoin transaction, we could make them more decentralized. Currently, when you send Filecoin via the glyph web interface, you sign the transaction, and then this transaction is transferred via HTTP to like a proxy server or a gateway server that glyph is operating. And then this server is running like a full Filecoin node and is broadcasting it to the Filecoin network via Gossip Sub. Now that we can connect any browser node to any GoLib-P2P node, we could do that ourselves. We could just have a web transport connection to some storage providers or some other nodes in the Filecoin network and use a JS Gossip Sub to put the message into the mempool directly. Another thing we could do is we might be able to make a Filecoin deal directly from the browser. Could connect to a storage provider using WebTransport, upload a file, do like all the stuff we need to do to sign the transaction, and do that without any other node being involved. This might also be interesting to retrieve the data later on from any IPFS or any Filecoin node. And Alex will present a short demo of JS-lib-P2P downloading a file from a Kubo node after this talk. Okay, to summarize, web transport, we shipped it in GoLib-P2P. It works. We can connect any browser node to a GoLib-P2P node. In Rust, it's currently not yet possible because there's no web transport implementation in Rust that's integrated into Rust lib-P2P yet. So now we've discussed how we can connect browser nodes to server nodes or standalone nodes in the network. There's one thing that we can't do with this set of protocols yet, which is connecting browser nodes to other browser nodes, and also connecting browser nodes to nodes that are behind firewalls. That's why we are working on WebRTC. WebRTC is a pretty old protocol. It's been standardized in 2014, and it's immensely complex. Like if you try to read the RFCs, you have a list of like 100 RFCs you need to read to understand what's going on there. It's really not fun. It's built for audio and video conferencing, and I'm sure everybody here in this room has used it many times when you do a Zoom call, when you do a Hangouts, like any of those video conferencing tools will use WebRTC under the hood. We don't need all these audio and video features, but there's also a reliable data channel called the RTC data channel in WebRTC. And we can use that to layer lib-P2P streams on top of those. If you're interested, they are using SCTP over DTLS over UDP. So that's some keywords to start your RFC search if you want to. WebRTC also, because it's built as a peer-to-peer video conferencing protocol, allows certificate verification by certificate hash. Like when you join a Zoom call, you don't need to get a TLS certificate, right? So that works, and it also provides hole punching capabilities. So you're able to establish WebRTC connections if you're in your home network and your router is blocking incoming connections. We split the WebRTC use case into basically two parts. One is the browser to server, and one is the browser to browser. For the browser to server, we built a protocol on top of WebRTC that doesn't require any stun and turn servers. There are more keywords for RFC searches. And we do an additional noise handshake there. The lib-P2P specification is almost done, and we also have implementations in JavaScript, in Go, and in Rust that are pretty close to getting merged, but they are still in review. Let's count the round trips here. First, we need to do a stun exchange. Then we need to do a DTLS handshake, which takes 2 round trips. Then we need to do the SCTP handshake, which takes another 2 round trips. And then we need to do our noise handshake. So we are back to 6 round trips here. So the same as WebSocket. It's not great, but it works. And if that's your only option, then you would be willing to wait 6 RTTs if the alternative is to have no connectivity at all. On the other hand, if you have the option to do web transport instead of WebRTC, you would of course choose that. Then for the browser-to-browser part, it's currently just a draft specification. We are working on it. I don't want to go too much into detail here because Max has another talk about WebRTC in particular. We are using our Circuit Relay v2 servers as coordination servers, and this will enable browser-to-browser connectivity. So what are the use cases? As I already mentioned, for the browser-to-server use case, it's a fallback when web transport doesn't work. And for browser-to-browser, we can potentially exchange files directly between 2 browsers, which is cool. And maybe very far in the future, we are not currently working on this, just an idea. Might be helpful in mesh networks that don't have any connection to the internet. So that completes our connectivity table. WebRTC, as I mentioned, it is in progress. It will be done very soon, and stay tuned for updates there. And if all of this sounds very complicated and confusing to you, don't worry. It is. That's why we launched a website, connectivity.libp2p.io. It explains everything and a lot more in great detail. So you can head there and really read what's going on if I'm connecting a standalone node to a standalone node or a browser node to a standalone node. And all these different combinations are explained there. So you can read it up. Yeah, thank you for your attention.